All right. Okay, so so a quick remark. Okay, the lecture notes are uploaded in the file section of the general channel. Okay, so I will link them in the class notebook after this class. Okay, but those who wish to in parallel look at the lecture notes, okay, I request them to use this uploaded copy in the file section of the general channel. Okay, so let's quickly summarize what we did last time. Okay, so if you remember, we sort of went over subgroups, subfields, subspaces. Okay, so recall that these are subsets of the parent space, okay, which themselves are groups, fields, or vector spaces themselves, right? And thereafter we discussed this concept of homomorphisms and isomorphisms. In particular, we discussed the idea of homomorphism between groups, fields, and vector spaces, right? And in particular, we said that if the homomorphism is also a bijection, okay, then it is an isomorphism, right? And this is true in the case of groups, fields, and vector spaces. Okay, however, we saw that in the case of simplicial complexes, and also in case of topological spaces, simplicial complexes as well as topological spaces, okay, the same conclusion is not directly true. Okay, one needs to ensure that both the forward map, so we need a homomorphism, right? We need a homomorphism, we need a bijection, right? This homomorphism should be a bijection. Okay, but this together does not imply that this homomorphism is an isomorphism. We also require the inverse map to satisfy some additional properties. Okay, inverse map also needs to be a homomorphism. Okay, so this is what we additionally required. Okay, in the case of simplicial complexes and in the case of topological spaces. Okay, so that is what I have written over here. So in this case, we sort of saw that if you have a homomorphism and if it's a bijection, then the inverse is also a homomorphism. So this followed, we could actually prove this, and because of this reason, homomorphism, which is a bijection, okay, one can refer to that itself as an isomorphism. Okay, so let me pause here for a couple of seconds. If there are any quick questions with regards to what we discussed, in the last class, this may be a good time to ask. Please raise your hand if you have any questions. Yes, Masavir, go ahead.
Yes, so while talking about the homomorphism, we said that the function is biject to itself. Now we're again talking if function is biject to, then there is the isomorphism. So I'm a bit confused about that.
Okay, see, the first is homomorphism, right? So homomorphism basically means that homo means, uh, you know, uh, um, same, okay, and morphism means that same shape, right? So like for example, in a group, right? So you have two groups, let's say G comma, so maybe I'll use the space below. So let's say you have G comma H, G comma plus and H comma product. Okay, and let's say we have a map that goes from G to H, right? We will say F is a homomorphism if F of A plus B is FA times FB, right? So if F satisfies such a property for all AB in G, we will say F is a homomorphism, right? This is the definition of homomorphism. Now, in the definition of homomorphism, we do not require this function f to be a bijection, right? So if in addition f is a bijection, right? So then we proved two things. First is that the inverse map, okay, f inverse is also a homomorphism, is also a group homomorphism, So this is something one can show. Okay, so what by that what I mean is you take f inverse of a dot b. So notice that this is the f inverse map. We take so maybe I'll write this as x y. So x y. So you take two elements x and y. you take their, you perform the binary operation between them. Whatever is the result, you take the inverse of that. One can show that this will be F inverse X plus F inverse Y, right? So one can show that. So this is true for all XY in H. Okay, so one can see that F inverse is also a homomorphism, right? And consequently, one can say that whenever we have a homomorphism and which is also a bijection, okay, then that F, one can refer to it as an isomorphism, right? F is an isomorphism and G comma plus and H comma dot, okay, are isomorphic. So isomorphic means that basically they are one and the same things, although if you look at them superficially, it may appear as if the elements are different and the operations that you perform over these elements are different. But there is a map which ensures that whatever you do on one side, okay, you do some analogous operation on the other side. Okay, so in some sense, these two groups are one and the same. Okay, so does that help you, Masavir? Does that answer it?
Yeah, actually, I think in the second lecture we defined this homeomorphism, which is a function which is bijective and which is continuous. Its inverse is also continuous. So if it's already
Yeah.
bijective.
Um, so that, see, I defined yeah, so there is some I mean, these words are one needs to use them carefully, right? So you are right that homomorphism and homeomorphism, right, those are different things. A homomorphism by default need not be bijective. Okay, I think that is the source of your confusion if I'm not wrong. Whereas when we talk of homeomorphism, the homeomorphism is a map that is defined between two topological spaces. Okay, so topological spaces will not be in some sense one of the focus areas of this subject over here. Okay, while I'll be time and again referring to topological spaces, it's fine if you don't understand them very well, because that will sort of take us very far away from the main topics of this course. Okay, so that's okay. So Masavir, you are right that when we talk of homeomorphic maps and homeomorphism between topological spaces, right, indeed bijection is inbuilt in the definition, but that's not the case with homomorphisms. I hope that clears your doubt. Okay.
Yeah, actually, I was confused the terms. I was considering homomorphism and homeomorphism the same.
Yeah, yeah. So I hope that is clear that homeomorphism is defined between homeomorphism in some sense is a topological isomorphism. Okay, so see, the word isomorphism should be thought of as trying to check whether two spaces, right, the space could either be groups, they could either be fields, they could either be vector spaces, they could either be topological spaces. So you can imagine any space. So whenever the space has some additional properties, we can ask, is one space same as the other space, right? So whenever there is some notion of similarity, so of course, see, this same and all these things, it depends on what we want to do, right? So depending on the context, what same means will change, right? Like, for example, in the context of group, right, same means something. In the context of field, same means some other thing, and so on and so forth, right? So whenever we have this definition of what same means, right, we can talk about isomorphism. So this homeomorphism, one can think of as a topological isomorphism. Okay, so I hope that helps. All right. Okay, so now we can advance with today's discussion. Okay, so the focus of today will be what are called as quotient spaces. Okay, and we will first begin by defining this concept in the context of groups, and thereafter we will sort of extend this idea to what are called as vector spaces. Okay, so in some sense, this will be the primary idea that we will be using in simplicial homology. Okay, so so maybe I'll say something at this point. It may appear very vague, but nevertheless, I want to say what we are going to do in the next few classes. Okay, so in the next few classes, starting from the next class, we will talk about officially this concept called as simplicial homology, right? So in simplicial homology, recall our goal was to, in some sense, identify how many holes are there, right? And in particular, we want to be able to distinguish between holes that are similar, holes that are different, and so on and so forth, right? In order to be able to do that, we have to make use of this idea of quotient spaces. Is that okay? So that's the relation and that's the purpose why we are going to study this quotient spaces, and this in some sense will be the primary idea, and you have to understand it very, very well, and this will enable you to understand what simplicial homology is all about, right? So you can see that this quotient spaces and all these things are defined from a very algebraic sense, right? And you will later on see that this idea of simplicial homology that we'll be talking about will also be defined in a very algebraic sense, right? So one can ask, oh, why are we using algebra? Because these holes and all seem something that is more visual in nature, right? Maybe something more geometrical would have been more appropriate. Well, the answer for studying this from an algebraic perspective is that, okay, we will see that we will be able to come up with nice algorithms to compute these, holes, to figure out, how many holes are there of different dimensions, are two spaces similar or not, and all these things we can do it algorithmically, okay? And that's the reason of having this algebraic, studying it from an algebraic perspective. All right. And okay, with this, let's begin our study of quotient spaces. Okay, so as I said, we will first study them in the context of groups. Okay, so what is a quotient group? So first, let me give a very intuitive explanation. Okay, very loosely, a quotient group is obtained from a larger group. Okay, so whenever I talk of quotient group, it means that I have a larger group or some original group that has already been given to us, right? From this larger group, we construct this quotient group, right? And how do we do that? By putting similar elements together, right? So we have been given some bigger group. Okay, we somehow define when two elements of this bigger group are similar. So all similar elements, we put them together, and whatever is the resultant, okay, that is loosely what is a quotient group, right? So one can ask, okay, how do we define this notion of similarity? Well, the similarity notion is defined via what is called as an equivalence relation. Okay, so I'm sure this concept of a relation, equivalence relation, and all these things, all of you must be familiar by now. But nevertheless, it is possible that you may have studied it some time back. So let's have a refresher course on what is a relation, and in particular, what is what is the meaning of an equivalence relation. Right, so let's begin by understanding what is a relation. Okay, so a binary relation, okay, between two sets x and y, right? So we have been given two sets x and y, and we say we have a relation between them. Let's denote this relation R. So this relation R is a subset of the Cartesian product x cross y, right? So let's say x has elements x1, x2, and so on, right? And y has elements y1, y2, and so on, right? So then the Cartesian product, okay, which is x cross y, okay, this can be defined as xi yj, such that xi belongs to x and yj belongs to y. All right. Okay, so this is how you define the Cartesian product, and we say that R is a binary relation if it is a subset of the Cartesian product, right? So the Cartesian product is made up of ordered pairs, right, whose first element comes from X and the second element comes from Y, right? So this is itself is a set. So you take any subset of this set, okay, that subset will be a relation. Right now, we will say if a pair x comma y belongs to R, right? So then we will write this statement symbolically in the following way, right? That x comma y belongs to R symbolically will be written in the following way, which says that x is related to y. Is this okay? So I hope what is a relation and what does this notation over here means, right? So R is a subset, and whenever you have a pair x comma y in R, we will say R is related to y. This is just some notation, right? Now a special kind of relation is this equivalence relation. Okay, so what is an equivalence relation? A relation R on X, right? So first thing, notice that when we talk of equivalence relation, we talk of a relation R on X, right? So the first thing that must strike you is, oh, well, when we talked of relations, we had two sets. What happened to that other set over here? Well, when we talk of equivalence relation, Y is also X, right? So in other words, for equivalence relation, we define R on X cross x. That is, R is a relation between x and itself. Okay, so that is the first thing. Hence we will say a relation R on x, which is supposed to be interpreted as a relation R between x and itself, right? So this relation R is a subset of the Cartesian product x cross x, right? So such a relation is said to be an equivalence relation if it satisfies the following three properties. The first is that it should be reflexive, symmetric, and transitive, right? So what does the reflexive property mean? It means that x must be related to itself. So every element little x in capital X must be related to itself, right? So R must include elements of the form x comma x such that x is in capital X, right? So all these elements should include, and it could include some other elements as well, but all these elements that is of the form x comma x, that must be in R, right? So that is the first property. The second property is the symmetry property. Okay, so this means that if you have a relation between x and y, right? So here both x and y lie in X, right? So x comma y lie in X, and we are saying that x is related to y. Okay, so which means that x comma y lies in R, right? So whenever such a thing holds, we require that y also be related to x, right? So notice that since I am writing this using round brackets, the order actually matters. Okay, so which means that this is by default or itself not equal to, okay, so this is not equal to y comma x, right? So since I'm writing with round brackets, the order matters. So x comma y is not equal to y comma x, right? So this property over here stresses that whenever x is related to y, we also require that y be related to x. Okay, so this implies that y comma x should also belong to R. Is this okay? For every x comma y, y comma x should also be in R. Okay, and last is the transitive property, which says that if x is related to y, right, and x is related to y and y is related to z, then we also require that x be related to z. Okay, which means that if x comma y belongs to R and y comma z belongs to R, okay, then we also we also require that x comma z belong to R. Okay, and then there is this important concept called as an equivalence class of an element, right? So basically you take an element x in capital X, right, and you collect all the elements in X which are similar to all the elements y in X which are similar to X, right? So the equivalence class of X, which is denoted by this square bracket X, this is the collection of all elements in capital X which are equivalent to X, right? And it is not difficult to see that. So let's say X be an element in X, right? So we know what its equivalence class is, right? And let y belong to y belong to the equivalence class of X. Okay, so that is y is equivalent to X, right? So one can then immediately see that this must also equal this. Okay, so here we have the equivalence class of y, which is basically the collection of all elements in capital X which are equivalent to y, right? And on the right hand side you have the equivalence class of X, but since y is equivalent to X, the equivalent class of y and the equivalent class of X are one and the same. So this is a set. This is a set, and the set over is defined in this fashion, and we are saying that these two sets are the same, which means the members of these two sets are one and the same, right? So let me pause over here. If you have any questions with regards to what is a relation, right, and what is a equivalence relation, and in particular what is this notion of a equivalence class, okay, this may be a good time to ask, right? So these will be the building blocks or defining building blocks for defining quotient spaces. So it is very important that you understand what these things are. Do you have any questions? Yes, Durjati, go ahead.
Sir, the equivalence class, can you give us some example to clear
So we will
the...
look at an example, and an example will be this idea of quotient groups itself. Is that okay? And we will look at some examples later on by what equivalence classes mean and so on. Okay, so for examples, maybe we can hold, and maybe if you have more questions, then you can ask it then. All right. Okay, so now we are going to define formally okay, so maybe I'll give a quick example because I realized maybe it may be difficult to understand. So let's say we have the set of integers, right? So let's say the set of integers is -2, -1, 0, 1, 2, blah blah blah. So maybe I'll put some dots over here, right? So we will say x is equivalent to y. So I'm defining this relation over here if y minus x so let's see, if x mod 2 equals y mod 2. Okay, so this is an equivalence relation. So Durjati, can you help me understand, okay, if you don't mind, what is this equivalence relation trying to do? So we have been given this z, right? So this is a set, right? And we are now trying to say that some members of this set are equivalent, right? So can you please help me understand which members are equivalent?
So the odd numbers and odd integers are equivalent, and the even integers are equivalent, like -2, 0, 2.
Very good, right? So that's all this is trying to say, right? So you have sorry, so you have this -2, what is happening? So you have this -2, 0, right? So all of these guys are 0, 2, 4, and so on. All these are equivalent, right? And similarly, what we are saying is that -1, 0, sorry, -1, 1, 3, 5, all these guys are equivalent, right? And now if I wanted to define this equivalence classes, right? So I hope you agree that the equivalence class of 0 includes -2, 0, 2, 4, blah, blah, blah. And similarly, the equivalence class of, let's say, 1 includes -1, 1, 3, 5, and so on, right? So what I'm claiming is that if you look at the equivalence class of 1 and if you look at the equivalence class of 3, they are one and the same, right? Because the equivalence class of 3 will be all elements that are equivalent to 1, equivalent to 3, right? So those again will be odd numbers because this is how we have defined this equivalence notion over here, right? So that's all I'm claiming. Similarly, this equivalence class of 0 will equal the equivalence class of 2. However, these two things will not be the same. Is that okay? So Durjati, does that quickly answer your question?
Yes, sir. Thank you, sir.
Okay. Is there any other question related to this? All right. So I don't see any raised hand, so maybe we can advance. Okay. So now we are in a, so you can see that we started off with a set. We define, define this notion of when two things are similar and so on. Right. So in that spirit, we can now talk about what is called as a quotient group, right? So what you should be on the lookout for is that what is the set here and how does one define the equivalence idea? Is that okay? All right. So in the quotient group, we begin with this group G, right? And we claim that this is an abelian group. So this is the larger set, right? And we are going to, say that some elements of this larger set are similar. And how do we do that? By defining an equivalence relation. Okay, so let's first see what is that equivalence relation. So let G be the given abelian group and let N be its subgroup. So which means that N is a subset of G, right? And N is a group itself, right? So N be a subgroup. Then we claim that N induces a natural equivalence relation R on G, right? And what is that equivalence relation? We will say two elements X and Y of G are related. In other words, X is equivalent to Y if the difference, that is Y minus X, this element lies in N, right? So notice that G, since it's an abelian group, okay, it comes with an operation. Let's denote that operation as plus, right? So let's denote it as plus, right? So what we are saying is that we will say two elements X and Y, okay? So these two elements are related to each other if you take Y and you take the inverse of X and you add them up, right? So Y minus X is equivalent to Y plus minus X, right? So this will be an element, right? Now Y and X, these themselves need not be part of N, right? So X and Y, so notice that you have G, and n is a subset of G, right? And what we are saying is that x comma y, this belongs to this group G, right? And we are saying that if the difference, that is y minus x, if this difference lies in capital N, okay, which is a subset of G, right, then we will say that x and y are related, or they are equivalent to each other. Okay, so to before we sort of define this quotient spaces, let's quickly verify that this relation that we have defined over here, okay, is indeed an equivalence relation. Okay, so which means that we have to verify that this satisfies the three properties, okay, that we discussed before, right? So the first thing we have to realize is that since n is a group, right, since n is a group itself, it should have an additive element, and it should be easy to see that if G is this group, right, G is the given group, so it itself must have an additive element, and the same element must also be an element, the additive element of n. Okay, so these things one can easily verify, right? So since n is a group in itself, it must have an additive element, and that additive element must be the additive element of G itself, right? So let's see if this relation that we talked about here is indeed satisfying the three properties, and we begin by verifying whether it satisfies the reflexive property, right? So we have to ask if every element in G, is it related to itself? That is, we want to ask, is A related to A, right? So in order to check whether A is related to A, let's go to the definition, right? So A is related to A if the difference lies in N, right? Now, what is the difference between A and A? So A minus A is 0, right? And since the additive element lies in N, okay, it trivially follows that A is related to itself, and since A was arbitrary, it is true for every element in G, and from this one can conclude that R is indeed reflexive, right? Now let's verify the symmetry property, and in order to verify this, suppose we will presume that there are two elements A and B in G and they are related, right? So by the definition, it automatically follows that B minus A lies in N, right? Now, since N is a group itself, right, B minus A should have an additive inverse, and that additive inverse should also lie in N, right? So the inverse of B minus A is minus of B minus A, and this is equal to A minus B, right? From this, it follows that this, since this lies in N, okay, it follows that B comma A, okay, B is also related to A. That is what I wanted to write. B is also related to A, and this implies that R is actually a symmetric relation. Okay, and finally we have to verify the transitive property. Okay, and for that, let's presume that A, B, and C are some arbitrary elements in G, and let's assume that these two conditions hold. That is, A is related to B and B is related to C, right? So this, by definition, we get that B minus A is an element of N and C minus B is an element of N. Now, since N is a group, right? If you take two elements which lie in N, and if you add them, that sum should also lie in N. So this means that B minus A plus C minus B should be an element of N, right? However, notice that here you have B and minus B, right? So these two things cancel off, and what we are left with is C minus A. So C minus A lies in N, right? And from that we can conclude that A must be related to C, right? So what we have managed to show is that if we have three elements A, B, C in G, and A is related to B and B is related to C, then this condition actually implies that A is related to C. And from this one can verify that R indeed is transitive, right? And hence R is indeed an equivalence relation. Is this okay? So let me pause here for a second or two. If there are any questions on how we verified whether this relation that we defined is an equivalence relation or not, this may be a good time to ask. Please let me know. Do you have any question? All right, so I don't see any raised hand, so maybe we can advance, right? So we have defined an equivalence relation, right? And now we can define the quotient space, right? So the quotient space is denoted in this fashion. So it's basically like G divided by N kind of a symbol, right? So of course these are sets here. So what does this mean? Well, this is defined in the following way, right? So you take every element in G, look at its equivalence class and collect all possible equivalence classes, right? And that's what this set is. That's how the set G quotient N is defined, right? So G quotient N is basically the collection of all possible equivalence classes, right? So this is the collection of all possible equivalence classes. Okay, so that's what this quotient thing is. And then we will define the addition operation on the elements of this set over here, right? So let this be an equivalence class here and let this be another equivalence class here, right? And we can define the sum between these two equivalence classes in this fashion. So this is a definition, right? So we are defining this operation in this fashion, right? So if I give you an equivalence class of A of A here and an equivalence class of B here, and if you wish to add them, what you do is you take the individual elements, right, and you add them up, right, and then look at the equivalence class of the final element over here. Okay, so one can then check that this set along with this addition operation is actually an abelian group, right? And this group, okay, is referred to as the quotient group. Okay, so let me pause here for a second or two. If there are any questions with regards to the what is meant by a quotient group, this may be a good time to ask. So the plan is that I'll now talk about quotient spaces in a very similar fashion to this quotient groups, and then we will look at an example, right, how this quotient space and all these things are defined. Okay, but nevertheless, if you have any questions on how we actually defined, the idea of a quotient group, this may be a good place to ask. Yes, Pankaj, go ahead.
Good morning.
Mm-hmm.
This addition in the quotient group, is it like union or the algebraic sum you're talking about?
What do you mean by union? This is how it is defined, right? Like for example, I hope you so let's look at this group. So I hope this is a group. You agree with this, right? Now let's say so let's take a so let's see so let's take a subgroup of this, right? So let's define E to be dot 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 minus 2 0 2 4 blah blah blah. So you agree that E is a subgroup of Z, right? E is a subgroup because it's a group itself, right? Pankaj, do you agree?
Yeah, yeah.
So this is the set of even numbers and Z is the set of all integers. I hope you agree that the set of even numbers is a subgroup of Z, right? And let's try to ask what will be Z quotient E. Okay, so this is the question that we are trying to understand now, right? So what we are defining is that two integers in Z are equivalent, right? So for X comma Y in Z, okay, X is related to Y if Y minus X belongs to E. Okay, Y minus X belongs to E. This is how we are defining the equivalence relation. Is this okay? So now, can one of you volunteer to tell me which two elements in Z are related? So I have defined the equivalence relation over here, right? So I have defined the equivalence relation over here. Can one of you volunteer and give me examples of two elements in Z that are related? Can one of you please volunteer? Please volunteer. It's okay if you give wrong answers as well. It's fine. I want you to volunteer, and make an educated guess. Yes, Durjati, go ahead.
Sir, minus 2 and 2.
Let's try to understand. Minus 2 is related to 2. Why is that? Because 2 minus of minus 2, which is 2 plus 2, which is 4, right? So 4 indeed lies in E, right? So indeed minus 2 and 2 are related. So how about minus 2 and 1? Okay, so let's ask this question. So 1 minus of minus 2, which is 1 plus 3. Okay, so sorry, 1 plus 2, which is 3. Okay, so clearly 3 does not belong to E, and that's why minus 2 and 1 are not related. Okay, so in this way you can see that all odd integers will be related, right? So odd integers, because 1 is related to 3, because 3 minus 2, 3 minus 1 is 2, and this belongs to E, right? So you can see that all odd integers will be related and all even integers will be related, and the quotient space over here, which is Z mod E, will actually be 0, 1. Okay, so now observe that in this there are only two elements. Okay, one is the equivalence class of 0 and the other is the equivalence class of 1, right? So can one of you volunteer and tell me why does this Z comma E only include two elements? Can one of you please volunteer and tell me why doesn't it include, for example, the equivalence class of 2? Why doesn't it include the equivalence class of minus 1? Yes, Ramkit, go ahead.
Because all even numbers should be equivalent to equivalence class 0 and all the odd ones would be equivalent to 1.
That's right. Okay, so very good. Okay, so notice that here what I said was this is the collection of all possible equivalence classes, right? All possible equivalence classes, right? And as Ramkit pointed out, right, this 2 is actually present in Z comma E because the equivalence class of 2 is actually the equivalence class of 0, right? So as I said, because of this equality, this is actually already included. Okay, so I want to include all possible equivalence classes, and this is the same as this, right? So I've already included this. So since I only want to include all different equivalence classes, okay, there are only two different equivalence classes, and this is how Z comma E would be. Now coming back to the question that Pankaj asked, so now what remains is to define an addition operation on Z comma E. So how does one define that? So I have to talk about what is this, what is this, what is 1 plus 0, and what is 1 plus 1, right? So what I'm claiming is that, well, this is the equivalence class of 0 plus 0. Now 0 plus 0, this addition is being performed in the original space. So this addition is defined in Z plus, okay, whereas this addition is being defined on ZE. Okay, this is being defined on the quotient space. So this is the definition and this is the answer, right? So 0 plus 0, we know how to add it in this original space. So 0 plus 0 is 0, right? And you look at the equivalence class of 0. Now what is this? Well, this is 0 plus 1, and 0 plus 1 in the original space is 1, and this is the equivalence class 1, and this is again 1 plus 0, which is 1, and this is 1 plus 1, which is 2, right? But the equivalence class of 2 is equal to 0, so you can see that this if you add this up, okay, this is the result. Okay, so Pankaj, does that help clarify your question?
Yes, yes, thank you.
Okay. Are there any more questions in similar spirit? Yes, Jacob, go ahead.
Is the relation always y minus x?
Is the relation always y minus x? You are asking, can it be some other complicated relation, like maybe y into y plus x into x, something like that?
Yeah, yes.
So you can define any relation that you want, right? So nobody is saying that this is the only relation. However, when we want to talk about quotient spaces, this is the relation that is of interest to us.
Why is it defined so? Like,
why is it defined so? The answer to this is that so this is some way of defining a similarity. Do you agree? This is some way of defining similarity. Now, I mean, of course, why it is defined this way, one cannot really explain in algebra, because in algebra, each of these things are abstract things. Is that okay? So one cannot answer this honestly from an algebraic perspective, but as we will see in in different applications, and the application of interest for us would be this simplicial homology, right? So you will be able to appreciate that by carefully choosing an appropriate this subgroup or a subspace, okay, we will be able to identify certain things as similar, and this will help us to not overcount the number of holes in a space. Is that okay? Not overcount or undercount the number of holes in a space, and it will ensure that we are not counting similar things as different objects. Does that make sense? Right. So when we look at an application, it may perhaps be clear, and for that you may have to wait until the next class.
Okay.
Okay, so I have not answered why is this defined in this way. However, when we talk of quotient spaces, this is the equivalence relation that is of interest. Is that okay? Now, why quotient spaces are interesting and so on, for that we will have to look at some applications, and the application of interest to us will be this, will be in the context of simplicial homology, and then things will become clear why we define and why are these quotient spaces of interest to us. Is that okay? All right.
Okay.
Are there any more questions? Okay, so I agree that at this point it will not be clear why we are using these things. Okay, so I admit to that, but nevertheless, one needs these tools, okay, and to be able to apply them later on. Okay, and from the next class, okay, I promise that we will talk about things from the simplicial homology perspective, right? And there it will make sense why we are defining these relations and so on and so forth. All right. Okay, so now I hope at this point, okay, this this quotient group should be clear, right? So the quotient group is obtained by taking this quotient space and defining this operation, and the operation is defined in this fashion, right? So I hope you agree that in this example that we considered, this quotient space is actually made up of only two elements, right? And we can define the addition between these two elements and so on, right? So you could have also said, oh, what I could have equivalently written this as ZE is equal to, let's say, 1 2, right? So you could have written in this fashion, right? So indeed you could have written in this fashion and nobody stops you, and the claim is that these two things are one and the same. The reason is that the equivalence class of 2 is the equivalence class of 0, right? So you could have written it in this fashion, and again the addition operation would have been defined in the same way. So 1 plus 1, okay, so 1 plus 1 is 2, so this will be 2. 1 plus 1 plus 2 will be 3, right? But 3 is equal to the equivalence class of 1, and similarly 2 plus 1 is equal to 1, and finally 2 plus 2, okay, this is equal to the equivalence class of 4, and this is equal to the equivalence class of 2, right? So the point I want to make is that it's up to you which elements which element do you want to make think of it as the representative of the equivalence class, right? So this equivalence class consists of infinitely many elements, right? And we are saying that we will identify 0 as the representative element, right? So I'm sort of labeling this whole set by one element. So why did I choose it as 0? This is only for convenience. You could have as well chosen 2, you could have as well chosen -2, 4, whatever you like. Similarly, here there is an equivalence class, and 1 is chosen as the representative element. So you could have as well chosen 3, 5, anything you want. But the point is that these are the only two possible equivalence classes. That is more important to keep in mind. Is that okay? And you can define this addition operation in this way. And whenever you define the addition operation, in order that this be viewed as a group, you have to ensure that the result actually looks like an element that lies in the original set. That's why even though we get 2, we write it in this fashion. Okay, this is just to enable us to visually see that the output of this addition operation, okay, is basically elements of this parent group over here. All right. Okay, so this is some algebraic stuff that we are discussing, but nevertheless I hope you are able to see what we are talking about, right? So now we have understood this concept of a quotient group. So now we will move on and discuss this concept of a quotient space, right? So whenever I write space, it has to be interpreted as quotient vector space. Okay, quotient vector space. However, quotient vector space is too big a word, so people usually call it as a quotient space, right? So again, the idea is similar, right? You start with some parent object. In this case, it's a vector space. So recall that a vector space comes with a field, okay, and an addition and a scalar multiplication operation, right? And let S be a subspace. So which means that S is a subset of V, and this S itself is a vector space, right? And for defining this quotient space, we define this relation R in the following way, right? So R is the relation where we will say two elements x and y of V, right? So x, y, where for x comma y in V, right? So for x comma y in V, we will say these two elements are related if the difference y minus x lies in S, right? So notice that I don't claim x and y themselves lie in S, but I'm saying that x and y lie in V, but the difference lies in S. So I hope this is clear. This is defined in similar spirit to what this quotient, the equivalence relation that we defined on the in relation to groups. Okay, so this is very similar, right? And as we verified previously, one can check that this R again is an equivalence relation, right? And now we have to define the quotient space, right? So this is defined in the same way. First, we denote this as V quotient with S, right? This is the collection of all possible equivalence classes, right? So you take every possible x in V and you look at its equivalence class, and you look at all possible equivalence classes, right? So this is again all possible equivalence classes. Okay, now this is right now only a set, right? This is just a set right now, and my claim is that we can actually view this as a vector space. Now, in order to show that this is a vector space, you have, you immediately can ask me, okay, tell me the field, tell me the addition operation, tell me the scalar multiplication operation. Well, the answers are as follows. So V itself was a vector space, so it must have come with a field. Well, whatever was the field for the vector space V, that is the same field for this new vector space that we are defining. So that answers the first question. Okay, now you can ask, okay, please define the addition operation for me. Well, the answer to that is give me two elements in this space, right? So equivalence class of x is one element over here, equivalence class of y is another element over here, and the addition operation is defined in the following form. So you'll first perform the addition of x and y in the original space, right? So this addition is in V. Okay, this is in V. So the original vector space must have come with some addition rule. So whatever is that rule, you use that rule to perform the addition. That will give you another element in V. Whatever is that element in V, you look at its equivalence class, right? So in this way, we can define this addition operation, and the scalar multiplication operation is defined in the following way. So you give me an element of V quotient S, right? So this is an element. Now you give me an alpha from the field, right? And the scalar multiplication operation, again, this is a definition. Sorry, again, this is a definition, right? So you first perform the scalar multiplication operation in the original vector space, and whatever is the output, you look at its equivalence class. Okay, this is how I define the addition and scalar multiplication operation, right? So you can see that you were given this original space, vector space V. From this vector space, we constructed another vector space by saying some elements are similar, right? And we use this special notion of similarity. So what was special about that? We made use of a subspace of V, and we said that two elements in V are equivalent if the difference actually lies in S, right? And in that way, we defined this equivalence relation, and we came up with these different sets of equivalence classes, right? And on that, we defined some addition and scalar multiplication operation, and we end up with a vector space itself. Okay, so maybe I'll now talk about an example of a quotient space, and hopefully that will make things a bit clear about what is happening over here. Okay, so let's go over it step by step. Okay, so begin with a parent space, and the parent space over here is R2, right? So this is the collection of the usual two-dimensional vectors. So I hope you agree that this comes with its own addition and scalar multiplication operation. And now I'm going to define a subspace of V, right? So what is the subspace? Well, it's the collection of all vectors in V which are of this form, right? Like for example, 1, 1, okay, this indeed lies in S, right? Similarly, pi times 1, 1, which is pi, pi, right? This also lies in S. Similarly, minus 1 over root 2, minus 1 over root 2, this also lies in S, right? So this is a subspace. I mean, I am stating that this is a subspace, and it's not very difficult to verify that it is closed under linear combinations, right? So you can verify this part over here. So since it's closed under linear combinations, one can show that indeed S is a subspace, right? So now we are going to define a relation R. So our goal is to define this quotient space, right? So in order to do that, we define this relation R, in which we will say two elements are related if, or two elements are equivalent if the difference actually lies in S, right? So X and Y, these are elements in capital V. We will say that X is related to Y if the difference Y minus X lies in S. Is this okay? So this is how we define this relation. So now let us try and understand pictorially, okay, what we are doing over here. Okay. So first let's try and understand what does it mean to say that Y minus X lies in S. So recall that S is the collection of all elements of the form alpha times 1 comma 1 for some alpha in R. Is this okay? This is how we defined S, right? So when we say Y minus X lies in S, what does it mean? It means that there is some alpha in R such that Y minus X is of this form. Is this okay? So there is some alpha in R such that Y minus X is of this form. Okay, so let's first try to understand pictorially what is happening, right? So you see these red vertical and horizontal lines. These are your X and Y axes, right? And this whole region is your R2, right? Now first let's try and understand where S is, right? So S is the set of elements which are of this form. So I hope you agree that if I choose alpha to be 0, I will get 0 comma 0. So this is the element over here, right? And similarly, 1 comma 1 and so on and so forth. So you can see that this collection of elements, right, this collection of elements that are over here, okay, this is S over here, right? And you can verify that this collection is actually a subspace. Is this okay? So this is a subspace. So first let's try to understand if all the elements in S are equivalent or not. Okay, so that is the question that we are trying to ask. Are all elements in S equivalent or not? Okay, so can one of you please help me answer this question? So the question is, if I give you two distinct elements in S, are they equivalent under this definition that we have? Can one of you please volunteer? Please volunteer. Yes, Jacob, go ahead.
Yes, if I take alpha 11 and beta 11 and
Very good.
And subtract them, then I get beta minus alpha 11. That is part of this.
That is part of S, right? So because of this reason, I hope you agree that these two elements are equivalent. In general, if you take any two elements, okay, on this S, I hope you agree that all of them are equivalent, which means that what I'm trying to do is I'm saying that all elements which lie on this S, I'm sort of, okay, so all elements which lie on S, I'm sort of saying that all of them are equivalent. Okay, so I hope you agree that S has infinitely many points. I don't care about them. All I'm saying is that all these infinitely many points in my eyes from henceforth will be equivalent. Is this okay? And I hope you agree that the equivalence class which represents this is 0 comma 0. My claim is that 0 comma 0 is basically S. Is this okay? So let me pause here for a second or two. If you have any questions on this statement or anything that we have discussed so far, please ask. Do you have any questions? All right, so I don't see any raised hands, so let's advance. Okay, so far what we have understood is that the collection of all these points are equivalent. Okay, and we can in fact use one equivalence class to represent all these points, and here is a representative element, right? So you take 0 comma 0, you look at the equivalence class of that, and this will be S. But I could have as well chosen 1 comma 1, right? So nothing would have stopped me. So I could have as well chosen 1, 1. Its equivalence class will also be S, right? So I hope this part is clear. Now let's take some other point. Okay, so without loss of generality, let's say 2, 1, right? So this is some point. I hope you agree that this 2, 1 does not lie in S, right? So 2, 1 doesn't lie in S because this is not of the form alpha 1, 1, right? So this is not of the form alpha 1, 1. Hence, this does not belong to S, right? So I hope this is clear that this point lies outside S. Now we have to ask what are the set of points that are equivalent to 2, 1? That is the question that we are trying to answer, right? So let's say x is 2, 1 and we want to understand what are the set of vectors which are equivalent to 2, 1, right? So let y be such what vector, and we will say x is related to y if y minus x belongs to S, which means that y minus x must be alpha times 1, 1 for some alpha. So which means that y must be of the form x plus alpha 1, 1 for some alpha. Okay, and these are if and only if conditions. So one can accordingly conclude that any element that must be equivalent to x must be of this form, right? It must be of the form x plus alpha 1, 1. So x is fixed and alpha is the parameter over here. So you choose any alpha, right? And whatever is the output here, that element will be equivalent to x, right? So from this one can see that if you take 2, 1 here, right? And if you look at the line which is parallel to this line, right? And you look at all elements on this line, those elements will be equivalent to 2, 1. Is this okay? So let me pause here for a second or two. My claim is that if there is any element on this line, okay, that element will be equivalent to 2, 1. I'll pause here. If you have any questions on this statement, let me know. All right, so I don't see any raised hands, so I presume more or less most of you have followed that why this whole line, the elements on this line are equivalent. Similarly, the elements of this line are equivalent. And in this way, I hope you agree that if I draw any line which is parallel to this, all elements of that line will all be equivalent. Is that okay? So now we can ask, okay, so what is the equivalence class? Right. So in order to identify the different equivalence classes, I'll choose the representatives of these equivalence classes, right? And in order to do that, what I'll do is I will draw this line over here. Okay, so this line over here. So this line, why have I drawn? Well, this is for convenience. Okay, there is no other reason, and there are several other possibilities as well, and we will consider such possibilities as well, right? So let's consider this line. Okay, so this is the line x minus y equals 0. Is that okay? So this is the collection of all vectors x comma y. Sorry, this is the collection of all vectors x1, x2 such that x1 minus x2 is 0. Okay, so this is the definition of this line. Okay, so now what I'm saying is that so I hope you agree that any line which is parallel to this green line, that will intersect this line over here. Okay, so that will intersect this line over here. So wherever is the intersection, you take that point as the representative for this equivalence class. Is this okay? So let me sort of elaborate this one more time. So let's say you take this line which is parallel to this green line. I hope you agree that all elements on this line are equivalent, right? And you take this to be the representative of the equivalence for this. Okay, so this is the representative. Is this okay? So this is the representative, and now what I'm saying is that, so here is what formally I mean, right? So what do I mean by what I have written over here, right? So what is V quotient S? Well, it's the collection of all equivalence classes, right? So what are the all possible equivalence classes? So for that, what I'll do is that I'll find a representative in this line that I had drawn, right? So what I'm saying is that you look at all possible equivalence classes where the representative is of this form, right? Where the representative is alpha times 1 comma minus 1 for some alpha in R, right? And this basically is equivalent to writing alpha 1 comma minus 1, and you look at the equivalence class of this for alpha in R, right? So I'm claiming that V quotient S is at the end of the day this collection of equivalence classes. So pictorially what I have done, I have this axis, right? I look at this line, okay? So this is the line, x1 minus x2 is 0, right? And I'm saying that you take any point over here, okay? You take any point over here and think of it as the representative for this entire line, right? So you think of this as the representative for this entire line, right? So this point over here represents the whole line. Similarly, this point over here represents the whole line. This point over here represents the whole line, right? So you identify this entire equivalence class by this point, this entire equivalence class by this point, this entire equivalence class by this point, and so on, right? And that's what I have written over here. Is this okay? So let me pause here for a second or two. I hope if you I hope you understood how we constructed this equivalence class and pictorially what is happening, right? So I have chosen some representative elements here. This is only for convenience. I could have as well chosen some other representative elements as well, right? But I hope you understand which set of elements are equivalent and how one can choose all possible equivalence classes. So this way of choosing ensures that we have chosen all possible equivalence classes. That is very, very important. Okay, so let me pause here for a second or two. Let me know if you have any questions. Okay, so I don't see any raised hands, so maybe we can advance. Okay, so if it's not clear, I mean, I've not done anything fancy. Okay, algebraically, it may look like I'm doing something very sophisticated. I'm not doing anything sophisticated. All I'm saying is that some elements are equivalent, and I'm combining all these elements and thinking of them as just one element. Okay, so this entire equivalence class. Okay, I hope you agree that this has infinitely many points. So all these infinitely many points, I'm thinking of them as one element in this space. Is this okay? So now one can ask, okay, this is a space and I can accordingly define some addition and scalar multiplication operation. So this itself is a vector space, right? So one can ask, okay, this is a vector space. How can I think of this vector space? Right, like what is the dimension of this vector space and so on and so forth. I can think about that, such questions, right? So my claim is that here is a situation where this idea of isomorphism is going to be very, very helpful for you, right? So if you think about this vector space, notice the elements look very, very complicated, right? So the elements, they are equivalence classes. So if you sort of visually look at this definition, okay, it will turn you off, right? It will say, oh, this is very, very complicated, looks very messy. But here is where this idea of isomorphism will help you, right? And let's think about that. So I'm going to define this function f in the following fashion, right? So let's see how I define that. So you give me an equivalence class, right? So an equivalence class is represented by this element over here. So you give me an equivalence class. Whatever is this equivalence class, I'm going to map it to alpha, right? So if it is alpha times 1 comma minus 1, the equivalence class corresponding to that, you give me this equivalence class as input to this function f. I'm going to spit out alpha. So I'm going to define this function in this fashion. Is this okay? So pictorially, what is happening? So recall, this is what was happening. So you had this x and y axis, and the blue line over here, okay, was basically, every element over here was acting as a representative, right? So every element on this blue line over here was acting as a representative. So you take any point on this blue line and map it on your x-axis, right? Map it on the x-axis. So that's what I'm doing over here, right? So you map it on the x-axis. Whatever is the element that you get, that is the output that I have written of this f function over here, right? Now one can very easily verify that this F is actually a homomorphism, and one can also verify that this F over here is actually a one-to-one and surjective map, right? And because of this reason, F is actually a bijection, and one can see that F is an isomorphism, right? So this is what we can verify. And for just to make sure that all of you understand what I'm doing, I'm going to verify one of these properties. In particular, I'm going to show that the way we have defined F, okay, F is actually a homomorphism. Okay, so let's see how to verify that it's a homomorphism. So the first thing you have to ask is, what kind of homomorphism are we talking about, right? So recall that this V comma S, this is a vector space, right? And this R over here, this is another vector space, right? So and F is a map that goes from V quotient S to R. So I am talking of vector space homomorphism over here, right? So in order to do that, what we have to verify, so vector space homomorphism is equivalent to linearity property. So we have to check if this F map over here is indeed linear or not, right? So let us take two elements in V quotient S. So this is one equivalence class. This is another equivalence class. So notice the representative elements are of a certain kind. Okay, so it is alpha times 1 comma minus 1, and the representative element for this next equivalence class is beta times alpha comma minus 1, and I'm taking their linear combinations. Is this okay? And if you recall, the way we define this vector space addition and scalar multiplication on this space, so from that it will be easy for you to see that so recall what we said. So this is how we had defined it, right? And similarly, x plus y was defined to be the equivalence class corresponding to the equivalence class of x plus y. So from that perspective, it is not difficult to see that lambda 1 times this equivalence class plus lambda 2 times this equivalence class must be lambda 1 times this vector over here plus lambda 2 times this vector over here, and whatever is the resultant, you look at the equivalence class corresponding to that. That's it, right? So this is what F is all about, and this can be combined and written in the following way, right? And what we have is F of equivalence class for this representative element. But F has been defined in a certain form. So whenever you have an element in this fashion, right, the output of this is just the coefficient multiplying 1 comma minus 1. So this is lambda 1 alpha plus lambda 2 beta, and alpha is the output of this equivalence class over here, and beta is the output of this equivalence class over here. So you can see that this relationship holds true, and from this one can conclude that F indeed is a homomorphism, right? And one can similarly check that F is a one-to-one map and F is a surjective map. Okay, so I will sort of encourage you to go over it step by step and make sure you understand why each of these steps are true, and from this one can conclude that F is a bijection, and from this we can conclude that F is an isomorphism, since F is a vector space homomorphism and it's also a bijection, and consequently F is a vector space isomorphism. So what we have managed to show is that these two spaces are isomorphic to each other. Okay, and symbolically we will write it in this fashion. Is this okay? That V quotient S is isomorphic to R, right? And this is the conclusion of this discussion, right? So if you recall, this V quotient S, sorry, this V quotient S, okay, looked very horrible for us, right? So this is how it looked, and after we chose these representative elements, this was how it looked, right? Alpha in R. Is this okay? So it looked very bad, but what we are saying is that, well, if you can construct a suitable function, you can see that this is actually isomorphic to R itself, right? So this is actually R. You can think of this vector space as R, right? So this is in some sense the main reason for using vector space isomorphisms and so on and so forth. Okay, so let me pause here for a second or two. If there are any quick questions, this may be a good place to ask. Okay, so I did a lot of algebra, but the algebraic notations may be a bit hard to understand at the first glance, but nevertheless, I would like to, emphasize that whatever I have done, okay, all of them are very straightforward in nature. You just have to, ensure that you understand how one step follows from the previous step. Okay, so as long as you understand that thing, it's not very difficult to see what I have done and why have I done it in this sense. Okay, so let me know if you have any questions. I'd be happy to explain things again. So some of them have not shown formally, but you can read it up, and if you have any questions, you are more than welcome to ask them, either during office hours or in the next class or whenever it is convenient to you. Okay, all right. Okay, so I don't see any raised hands, so maybe we can move on to the next discussion, right? So there is a theorem over here. Okay, I'll state this theorem, and this will be something that you will have to verify as part of your homework, right? So now one can talk of direct sums between quotient spaces, right? So we know direct sums of vector spaces, right? And in that same spirit, we can now talk of direct sum of quotient spaces. Okay, so let's just read the statement of the theorem. So we have been given two vector spaces. So V1 and V2 are two vector spaces, right? They can be completely unrelated to each other, but they need to have the same, the field for both V1 and V2 must be the same. And let S1 and S2 be two subspaces of V1 and V2 respectively. So S1 is a subspace of V1. Similarly, S2 is a subspace of V2. Right, so we recall, we know how to define this direct sum V1 V2, right? So this direct sum is basically you take all these ordered tuples V1 V2 such that V1 lies in capital V1 and V2 lies in capital V2. So this is how we define this direct sum. Sorry. So this is how you define this direct sum over here, and this itself is a vector space because one can define this addition operation between individual elements in this set, and we can also define a scalar multiplication operation, right? So this is a direct sum, right? So now what this theorem states is that, okay, you take the quotient of V1 with respect to S1 and you take the quotient of V2 with respect to S2. So this is a vector space, this is a vector space. You take their direct sums. Okay, so this is a vector space, this is a vector space, you can take their direct sums. This itself will be a vector space, right? This itself will be a vector space. Now what this theorem says that this resultant vector space is isomorphic to this vector space over here, right? So let's just try and understand what is there on the right. So you first take the direct sum of S1 and S2. So again, S1 is a vector space, S2 is a vector space, so you can talk about the direct sums of S1 and S2. And similarly, V1, V2 are vector spaces, so you can talk about their direct sums, right? So this is a direct sum, this is a direct sum, and you can talk about their quotients, right? So one can in fact verify that S1, a direct sum S2 is a subspace of V1 direct sum V2, right? So this is a vector space. Okay, this is a vector space, and one can view this S1 direct sum S2 as a subspace of V1 direct sum V2, right? One can view it in this fashion, and one can now talk about the quotient of V1 direct sum V2 with respect to S1 direct sum S2, right? And the claim is that this direct sum is isomorphic to the vector space to the quotient space obtained by taking the quotient of V1 direct sum V2, okay, with respect to S1 direct sum S2, right? So I won't give the proof of this in this class, but I will sort of give you sort of the broad idea, and I encourage you to go back home, right, and do it on your own, right? So here is the idea. To show something is two vector spaces are isomorphic to each other, what is the idea? You have to come up with a function, right, which is a homomorphism as well as a bijection. Okay, this is what you need to show. So here is that function. So I'm giving you the function, but I leave it to you that for you to verify that this is indeed a homomorphism and a bijection. So what is this function? This function will go from this direct sum to this quotient space on the right? And what will this function do, right? So recall that this direct sum, okay, will be ordered tuples of elements from the first space and elements from the second space, right? So this is belonging to V1 direct sum S1. This is an element in V2 direct sum, V1 quotient S1, and this equivalence class is an element of V2 quotient S2. Is that okay? So this is what is there, and this ordered pair is an element of this direct sum over here. So you give me an element in this fashion to this function phi. What will this function do, right? So what we will do is you take the ordered pair v1 v2. So I hope you agree that v1 v2, this ordered pair, this lies in v1 direct sum v2, right? And what you do is you look at the equivalence class of this element with respect to this subspace, right? And whatever is that, that is what will be the output of this function phi, right? Now the first thing, so this is what your homework is going to be. This homework will require you to verify that this function phi is actually well defined. Okay, so well defined means that every element in the domain is actually mapped to only one element in the codomain. Furthermore, okay, so this is something you need to verify, and furthermore, okay, you need to verify that the definition does not depend on the representative chosen for the equivalence class, does not depend on the representative chosen for the equivalence class, chosen for the equivalence class. Okay, so what do I mean by that? So notice that here we choose the equivalence class associated with v1. So it is possible that, you know, there is some v1 prime, okay, which is equivalent to v1, and I could have as well chosen v1 prime to be a representative of this equivalence class, and similarly I could have chosen v2 prime to be a representative of v2, the equivalence class of v2, right? And I could have similarly applied this map over here, right? And what we require is that at the end you get the same output, right? So the definition says that v1, the output would be the equivalence class of this, and what you need to verify is that these two things are actually equal. Okay, these two things are actually equal, that these two equivalence classes are same, and which requires you to verify that v1 v2 is actually equivalent to v1 prime v2 prime. Okay, so again, this is algebraically it may look very hard, but it's not very difficult. And separately I want you to verify that this function phi that we have defined is actually a homomorphism, and this is a bijection, right? So if you actually verify this, you'd be able to conclude that indeed this direct sum is isomorphic to the quotient space that is written on the right. Okay, so let me pause here for a second or two. If there are any questions with regards to what is being asked of you to prove. Okay, so this will be part of your assignment 1. At some point I will put all these questions together and upload it to your team's channel. Okay, but these will be the different questions in your assignment. Okay, so if you have any questions with regards to what I have asked in this question, please ask, and then we will move on to the last discussion for today. All right. Okay, so I don't see any raised hands. So maybe we will discuss the last theorem of the day. Okay, so the last theorem of the day says something like this. Okay, so let V be some finite dimensional vector space, and let S be a subspace of it. Right. So V is a vector space, S is a subspace. So this is a vector space itself. Then the claim is that the dimension of the quotient space equals the dimension of the parent space minus the dimension of the subspace. Okay, so let's try to verify this, if this is indeed true or not. Okay, so we have been told that V is a finite dimensional vector space. Okay, so without loss of generality, let us assume that V is some n dimensional space and S is its subspace. So let's say S is some k dimensional vector space. Right, so V is a n dimensional vector space and S is a k dimensional vector space. So from this it automatically follows that dimension of V is n and dimension of S is k, and what we have been asked to show is that dimension of V quotient S is actually n minus k. Okay, so this is what we have been asked to show. Right, I hope you agree from your course on linear algebra that one way to check what is the dimension of a vector space is to identify a basis for this quotient space, right, and see if it has n minus k elements or not. If it has n minus k elements, then one can immediately conclude that the dimension of V quotient S is indeed n minus k, right? So, this is what we are going to do. So we are actually going to come up with a basis for V quotient S, and we will show that it has n minus k elements, right? So let us see how we can do that, right? So we know that S is a k-dimensional space, and this is a subspace of V. So since S is k-dimensional, it must have a basis, right? And this basis must have k vectors, right? So, and let's say we represent these vectors as V1, V2, all the way up till Vk. Right, so these k vectors together form a basis for S. Right, now in linear algebra, we studied that if we have a subspace of V and this is a basis for S, we can extend this basis into a basis for V. So what do I mean by extend? Right, we can add some additional vectors to this collection of vectors. So notice that V1 to Vk is already there, and we can add some additional vectors and form a basis for V. Right, so since the dimension of V is n, the number of vectors in this collection must be n in number, and the first k vectors, they form a basis of S, right? And the remaining n minus k vectors, when they are combined with this collection over here, the resultant collection is a basis for V. Okay, so this is the result of linear algebra, and okay, this is something that you should be able to verify on your own. All right, so now what we need to verify is that the dimension of the quotient space is actually n minus k, right? And as I said, in order to show this, it suffices to show that this quotient space has a basis with n minus k elements over here, right? So first let's try to identify such a basis, right? So first let's try to identify such a basis or guess such a basis, and then we will show that it spans this V quotient S, and indeed it's linearly independent. Okay, so that's what we are going to do, right? So in order to guess a basis for V quotient S, so recall what V quotient S is. V quotient S is the collection of all equivalence classes in for elements in V. So this is little v and this is capital V, right? So let's try to understand something about this equivalence class over here. Okay, so for this, let little v be an element of capital V, right? So this is what we are assuming. Since little v lies in capital V, and since V1 to Vn is a basis for capital V, I hope you agree that I can write little v, okay, as a linear combination of V1 to Vn for some alpha 1 to alpha n, right? Next, what I do is I define this V prime vector. So what is this V prime vector? This V prime vector, okay, is a linear combination of Vk plus 1 to Vn, and the linear combinations includes alpha k plus 1 all the way up till alpha n, where these scalars actually are the scalars that were used in the definition of V, right? So I hope you agree that V will be alpha 1 V1 plus dot 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 alpha k Vk, and then it will be alpha k plus 1 Vk plus 1 plus dot 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 plus alpha n Vn, right? So whatever is this last part over here, you take that and define that to be the vector V prime. And my claim is that this vector V prime is equivalent to V, right? So again, one has to ask, what do I mean by the equivalence? I mean that V minus V prime actually lies in S, right? So actually lies in S, right? So can one of you please volunteer and tell me why does V prime V minus V prime lie in S? Can one of you please volunteer and tell me why does V minus V prime lie in S? Why does V minus V prime lie in S? Yes, Jacob.
When we do the subtraction, only the first k vectors remain.
Yeah, their linear combination we end up with, and we know that V1 to Vk is a basis for S. That's it. Very good. Is this okay? So it is easy to see that V minus V prime is something like this, and this actually lies in S, right? So from this we can conclude that V and V prime are equivalent, and in general, for any V, if you construct this V prime, the equivalence class of V must equal the equivalence class of V prime, right? Because V is equivalent to V prime. So this automatically implies that the equivalence class of V and the equivalence class of V prime must be the same, right? So that's what I have written over here. The equivalence class of V must equal the equivalence class of V prime. And what is V prime? Well, it is alpha k plus 1 Vk plus 1 all the way up till alpha n Vn. Is this okay? So this is what we have. And if you look at the equivalence class of this, what is it? Well, my claim is that if you remember the way we had defined this addition and scalar multiplication operation on this quotient space V given S. So from that definition, you can see that, well, the equivalence class of this must equal the equivalence class that is given over here. That is alpha k plus 1 Vk plus 1 plus dot 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 plus alpha n Vn. So what we are managed to show is that any equivalence class, so V is an arbitrary vector, any equivalence class must indeed be of this form over here, right? So any element in V quotient S, one can write it in this form, right? Where you are free to choose alpha k plus 1, alpha n, all the way up till alpha n. So all these things you can choose, right? So from this it follows that the equivalence class of Vk plus 1 to the equivalence class of Vn. Okay, so all these equivalence classes, they span V quotient S, right? So I hope this is clear that any equivalence class, okay, can be written in this fashion. And because of this reason, one can conclude that this actually spans V quotient S, right? So now all that remains is to show that this collection of equivalence classes is linearly independent, right? And in order to do that, we will make use of proof by contradiction. And for that, what we will assume is that suppose there exists some scalars beta k plus 1 all the way to beta n, not all 0, such that this linear combination, okay, gives rise to the equivalence class whose representative is 0, right? So why am I choosing this element over here? Well, in order to show linear independence, right, recall what we said, right? So we claim that vectors x1 all the way up till xn are linearly independent if there exists no collection alpha 1 to alpha n such that this linear combination equals 0, right? This should never occur. Now instead of using 0, notice I write the equivalence class of 0. Why do I write that? Well, you can check that this actually is the additive identity of this vector space, right? So you can actually check this. That's the reason it suffices to check if that there exists no all non-zero scalars beta k plus 1 to beta n such that this is 0. And since we are going by proof by contradiction, okay, we will presume that such a thing actually exists, right? Now from this idea of how we do this addition on this quotient space, this must equal the equivalence class of this combination over here, right? So the equivalence class of this combination must equal the equivalence class of 0, right? So when we say two equivalence classes are the same, it means that this element over here must be equivalent to this element, or this 0 must be related to this element over here, right? So if one says this, this automatically implies that if you take this right hand side and subtract 0 from this must lie in S, right? And I claim that this actually leads to a contradiction. Why does it lead to a contradiction? Because this implies that this linear combination lies in S, right? So which automatically implies that this linear combination must equal the linear combination V1 to Vk for some C1 to Ck. However, you cannot have such a relation. The reason being that we know that V1 to Vn is a basis for V, which means that V1 to Vn is linearly independent. So since they are linearly independent, you can never have such a relation. So this leads to a contradiction, and from this one can conclude that these equivalence classes are linearly independent, and from this it follows that the quotient space has this as the basis. From this one can conclude that the dimension of the quotient space is indeed n minus k. Okay, so let me stop over here. I'll be available for a few more minutes, and you can feel free to ask me any question that you may have.